4.7, number 344. Find the largest volume of a cylinder that fits into a cone of base radius r and height h. All right, so this is the most abstract form we have exhibited so far. You notice there's no numbers in the problem. It's a tricky little problem. So let's demonstrate how to go about it. The picture will probably help immensely. So I'm going to draw something here resembling this example. Okay. I'm going to draw a cone. All right, there's a cone for the most part. And there's a cylinder inside. Now this cone, there's a lot to keep in mind in a problem like this. So this cone has a radius which is fixed, all right? It may seem totally obvious, but it's something to keep track of. The radius of the cone is fixed at cap r, and the height here is fixed at lowercase h. I'm going to draw it on the outside because it's going to get messy in here in a second. So I'm going to draw this on the outside. Hopefully it'll be clear enough what it represents. Okay. So the height, right, there's the height of the cone. And those cannot change out the problem. Those are constraints on the problem because they are fixed, and so therefore they will play a role in the constraint equation that we'll attempt to construct here momentarily. Now we have a volume, we have a cylinder in here whose volume is changing. Now I'm going to draw one representative cylinder in here, right? This is not a fixed cylinder. This is just one way the cylinder might appear, right? So I'll just draw here maybe. Here. And map that down. Maybe something like that. It's not the best, but you get the main idea. All right. So we're supposed to find the largest volume of the cylinder. I need some dimensions on the cylinder, though. So maybe I'll call the radius of the cylinder little r. Okay. A little confusing. I wish they would not have used little h for the height of the cone and cap r for the radius of the cone. They should have used similar casing for the cone, but whatever. So I'll use little r for the cylinder radius, or maybe I'll put a little c there to keep track of it, rc. And then we have the height of the cylinder, which I guess we could put here maybe. I'll put it out here. Right there. I'm just going to put height c. Because if I use cap h, I'm going to get confused with cap r being for the cone and cap h being for the cylinder. I'm easily confused. All right, so I'm just going to use h sub c for the height of the cylinder. All right. So the height of the cylinder and the radius of the cylinder will have something to do with the objective function because I'm trying to maximize the volume of the cylinder. So right away, we should be able to say, if nothing else, that volume of the cylinder, and this isn't that descriptive, right, because cone also starts with C, but hopefully we'll keep track of it. Okay, so volume of the cylinder is what? It's just pi r squared. Now what's r? It's a little r, right? Little r. Pi r squared times h cylinder, right? It's just the base, which is a circle, so pi r squared, times the height of the cylinder will give the volume of the cylinder. Okay? Now, as I was saying before, these are changing. The radius of the cylinder and the height of the cylinder are changing, because you can imagine, for instance, if you were to compress the cylinder downwards, then its radius would increase, right? Because it's able to reach to a deeper part of the cone, in a sense, right? Up here it's trapped at a smaller radius. But as you compress the cylinder downwards, it would reach out further with its radius, but its height would be constricted. So the volume would change because the radius would grow, but the height would shrink if you were to compress the cylinder further downwards towards the base of the entire cone. But if you were to raise the cylinder higher, meaning the walls of the cylinder higher, then the radius would decrease, right? RC would decrease because it's moving higher into the cone. It's more constrained inside here. You'd have a smaller radius, but yet you'd have a higher height for the cone, right? It'd be taller, and that would create, again, a different volume for the cone altogether. So at the extremes, if you think about the extremes, if you were to compress the cylinder all the way down, h would be 0, and the radius would be the same as the radius of the cone, right? RC would become cap R, and HC would become 0, and that product would be 0. So at that extreme, right, when the radius is as large as it can be, that is RC, which is trapped between nothingness and radius of the cone, when the radius of the cylinder becomes the radius of the cone, you've squished the whole cylinder to the bottom of the cone. It has no height whatsoever, and you'd have a 0 volume. So too, if you extend the height of the cone, right? The height of the cylinder until the height of the cone, right? Which is as high as it can get, really. You're not allowed to go outside the cone. If you do that, if HC becomes the height of the cone, then the radius of the cylinder, the radius of the cylinder goes to 0. Right? As the height increases for the cylinder, the radius of the cone decreases because it's more constrained inside the peak of the cone. So therefore, at that extent, height becomes maximal at height of cone, but yet the radius of the cylinder becomes 0, and again you have a product of 0. So therefore, at the two extremes, where the cylinder is as high as possible, or as tall as possible, I should say, and the cylinder is as short as possible, at those two extremes, the volume is 0. So therefore, we anticipate that probably somewhere in between, there will be a maximal volume for the cylinder at some intermediate place inside the cone.